Hi, I'm Ryan Nickel, CTO at DSA Ocean, and today I want to take you through a subsurface mooring design and analysis process using the ProteusDS Oceanographic toolset. So we are going to start with Oceanographic Designer. Now, you get a little prompt here asking to start a new project or opening an existing one. I definitely encourage you to consider old projects that you have and even the sample mooring files that we have on our website. Often these can be adapted for different water depths for your own project. Of course, you need to check and see how they behave and evaluate their performance, but it's always a good starting point to use something that's existing. But for this example, we're going to start with a brand new project. And we're going to, it's all arbitrary, it's not a real project, but we're going to just pick 1,000 meters water depth. There's a few other options here for the lat and long location. That's totally optional, and you can always change any of these parameters later. It's very, very easy. The next step is picking the mooring type, so surface, taut surface, or subsurface. And again, you can change this later. It's not a problem to do that, but it does sort of give you a bit of a starting point to work with. And we could just create this right away, but it's also possible to pick a starting float that you want to work with. So for fun, I'll just kind of demonstrate. If we pick a smaller one, just 33-inch, 750 meter depth rated float, and go from there. And so now we're going to work with a target depth for this top float at 250 meters. So we'll adjust that in a moment. But I will show you a little bit more about what's going on here. So in Oceanographic Designer, this is your main mooring design window. And we can add a line or add components. Now we've already got a line here that we can adjust the length in here, and then there's an assembly called top buoy, and you can delete these and make your own if you want. We'll get into some of those details shortly. In the assembly view here, you can see we've got our little float, and now there's this puzzle piece window here for that individual component in here, and this is one thing I want to check on. So this allows us to add attachments, particularly to the subsurface buoy. And as it's an ADCP buoy, we actually want to get an ADCP in there. So we might pick Teledyne Quartermaster, for example. And the interesting thing about this is that the weight is going to be incorporated into the net flotation of this system. So if now we do have to select this flow opacity. There's another video tutorial on that, but essentially what this means is how much of it is sticking out of the buoy for the purposes of drag calculations behind the scenes. And my rule of thumb is just pick something like 10%. To get a little bit extra drag, but most of it's sitting inside the float there. So, and as you can see, the total weight of the assemblies, the wet weight's been reduced a little bit, so we get a little bit less flotation. Now you can see an estimate of the top tension and an estimate of the anchor tension. This is a little bit low on the anchor tension, so it's kind of looking like this preliminary design here that we've got. We're maybe getting a little bit low, close to the threshold of zero tension. If we do cross that threshold, we'll start seeing NA in the estimated depths here. NA just means it's the Oceanographic Designer is not able to do a very basic calculation on static weight and buoyancy from the uplift. The wire is too heavy for this buoy is essentially what it means. And then we need to use a larger float. It's that simple. But yeah, like we said, we're going to aim, just again arbitrary for a little project here, we're aiming for 250 meter depth, so we'll increase the line length here to 750 meters, and there you go. So just looking at this, the total wet weight of the wire here is 106 kilograms, and I mean you can just see that's why it's why it's causing a problem here, because it's greater than the uplift for the float. So the short story is we need to get a bigger float. Just that's what that's telling us right here. So what we'll do is we'll pick a bigger float. Now we've got a search here, a very basic search. Just type in ADCP, and then we have a couple of different options here. Why don't we pick, say, a 44-inch float? Well, we've got one 44-inch there. And oh, there we are, 44-inch, 750 meter depth rated. We'll pick that one. Now you will need to add the quartermaster into it again. There we are. And we'll set the flow opacity to 10%. Okay. And we don't need this old one anymore, so we'll just delete that. Yep, delete from the assembly. And you can see we got quite a bit more uplift here. And then, of course, it's able to resolve the estimated depth for the components there. So that's good. And you can see the anchor tension's gone up and the top tension's gone up. So, things are looking good. Always a good idea to save the project. So let's just save this file here. Call it Subsurface Mooring. Subsurface 1000 meter. Save. Okay. So I'll show you how to do a bit more detail on how the official parts library works. So we'll add some connectors here. Connector assembly A. I like to use connector assembly A and B just for different sort of combinations of connectors. So clicking on this plus here in the subassembly window for this is going to open up the official parts library. Click on connector, and there's tons of different commercial suppliers here. So we'll pick safety anchor shackle, and it's pretty common to use the 2-ton 1/2-inch shackle. So we've got it here, and we could duplicate this. That's great. Maybe just highlighting a bit more detail on the connectors here, and we'll put a sling link between the two of them. But just note, here you can see the working load limit and the web link where you can find the spec sheet that we got this from. It's all available online, publicly available information here. You can see the sling link from Crosby, and there's lots of information there. And if you want to see different units for the inputs, it'll automatically convert them for you, so you don't have to do any mental math for all that. So we'll click on the sling link here. I want to reorder it, so we go shackle, link, shackle. That looks good. Now over here we can use the duplicate button, and then we have the connector assembly A again down here. So we're starting to build out the detail in the mooring, and things are looking good. So later you can, if you want, you can create a bill of materials and assembly layout in one file. Just a very, very, very super simple schematic view in here, just showing a bit of a drawing with the general layout of the top buoy and the connector and the wire, which is nice to see. And let's edit the environment here. We're not changing the water depth or anything, but we can change the current profile that we want to evaluate the system in. So I just want to I'm going to keep the surface speed at 1 meter per second, but I'm going to adjust this value here. So depth at water column 1000, and we'll just put it to 0 here. And it's linearly interpolated between the points. So this is the same as a linear shear profile. And we can add other ones if you want to explore different scenarios, but for now we're just going to use this one. So now we've got a little mooring configuration here. The next question is, well, how much is the mooring going to deflect in this current profile? And get some feedback on that. Maybe we want to limit the knockdown to 10 meters or something like that. And so we'll just first see what happens when we do this. So first we click Analyze, and we want to go static. And we're only looking at one current profile. So we open one ProteusDS simulation toolbox. So this is our engineering physics solver tool that runs the simulation. It's created, Oceanographic Designers created all the files, the numerical mesh for the mooring and everything for us, so we don't need to do anything. There you can see there's the mooring, the numerical model of the mooring ready to go, and we will just hit run. It's got the current profile in here, everything's ready to go. All we need to do is tell it to run the analysis. So it's pretty simple mooring, so there shouldn't take very long to run the static analysis. It's an iterative process, and so you don't always get a lot of feedback on what's happening as it's iterating through the analysis process. But for something like this, it shouldn't take too long to do. And once the analysis is done, it's all done. Once the analysis is done, I always for the first time, I like to do a visual reality check in 3D. So we'll open up Post PDS here from the Proteus Simulation Toolbox window. So we have a nice 3D view of the world. There's some clouds and the sea and everything like that. One problem is that it's kind of hard to see the mooring because it's 1,000 meters water depth. and what you can do is go to display type and change it from rendered to engineering view. What's nice about this is that it then shows the mooring in 1 pixel thickness all the time. You may notice it's still a little bit faint, and what you can do is go to settings and turn off any fog below the water, and then you can just see everything very well. So there's our whole mooring. That's the starting position. Now the other thing is, this is in perspective view. You may find orthographic view is a lot easier to work with. Let's just make this a little bit bigger to get a look at what's happening, because you get a nice side view of the system. So if we go back to, let's pick orthographic, and I'll go back to select camera preset east. By default, with the current direction heading north, that means the current will flow from the left to the right. So we've got the seabed, you can see here, the sea surface, it's at 200 meters water depth here. So this is the initial position of the mooring. The first calculation step it'll do is calculate the stretch of the mooring in no current, and because it's wire, it's very stiff, there's barely any change in the elasticity. And then we see the deflection of the mooring in that current profile that we've got. So that, that looks about right, just very generally. We had a reasonable amount of tension, but not a lot. And you can see there's some reasonable horizontal deflection. And what I want to know though is also the vertical knockdown, and just get a handle on how much that is. So it looks okay, but we want to see actual numbers on this. So I would now click on the Oceanographic Report tool. And what I like to do is keep an eye on any subsurface buoys, the main flotation that I'm interested in. That'll show up in the summary page, and you just go generate. And then it'll say, do you want to open up in Excel? So we'll open the formatted report in Excel here. Note later, if you like, you can always change the units for the report after the fact, which is really handy. Anyway, we got some safety factor checks here. The loads are all very low. We're not seeing anything exceeding safety factors. That's great. Honestly, what most of the time I spend looking at is deflections. So here we are, horizontal excursion. Now here, this is what we picked. We just wanted to see on the summary page the ADCP sphere at the top. And you can see the maximum horizontal excursion is almost 200 meters. So, the horizontal excursion is one thing, but vertical knockdown is another factor here. So vertical excursion, this is more about this is sort of a little bit more related to depth. And in fact, you can see the depth is the same here. The difference is just if there's water level offsets or waves or something like that, you'd see differences between those two. But really what's interesting here is this knockdown value. So knockdown is a relative vertical measurement from the calm water condition. You can see we're at 30 meters knockdown. That can be a problem also, just accounting for the ADCP range from the surface, and there's issues with data quality and things like that. There's also tilt to keep track of, but what's of interest here right now is the knockdown value. So let's say that's too much knockdown. One of the things you could do is change the float size again. So maybe what we'll do is we'll close this report. The workflow is all one way, so we'll just close everything. You can save a copy of the report if you want, but we go back to Oceanographic Designer here. If you want, you can save a different copy of this. What I'm going to do is actually, so we got a 44-inch sphere. Let's find something bigger. So we'll go back here. I believe there is a 49-inch here. And now we'll add the ADCP back in as well. So we were looking at a quartermaster. So we'll select this and set the flow opacity to 10%. Okay, now you'll see the top tension is 4.6 kilonewtons, 3.5. So this is, the higher the tension, usually the less knockdown you're going to get. Of course, that means we need a bigger anchor and so on, but that's another story. So we'll save it and then go through the analysis process again. It does say, hey, there's a folder here already, and it's going to erase the content. So just be aware of that. I'm okay with that. For this particular case, we'll do the same thing, run it again. And we'll just need to wait while the static analysis goes through its process again. And it's done. So we'll open this result in Oceanographic Report tool here. I'm going to click for the summary to look at the subsurface buoy. Yes, we'll open the report. And again, the loads go up a little bit, but I'm not expecting to see any issues with component strength, and we don't. Now for horizontal excursion, instead of almost 200 meters, now we're down to 128, so that's kept things under control. Vertical excursion is keeping quite a lot closer, and of course instead of 30 we're basically at 12 meters knockdown, so it improved there by quite a bit for this loading scenario. And of course, if you want to take a look at anything more closely, you can look at the separate sheets for line tensions and inline and attachment tensions and component positions and things like that, and get into a lot more detail if you want to. So that's what I wanted to do, is take a quick run through what a workflow might look like with subsurface mooring design. Thanks for watching.